iC-Haus Integrated Circuits.
Hello and welcome to our today's webinar on laser tools. iC-Haus offers a variety of laser diode drivers which are capable of producing single-digit nanosecond laser pulses. On the lower end of the drive current range, we have the two-channel drivers iC-HK and HKB, the latter for blue or direct green laser diodes. HK and HKB can drive up to 700 milliamps of laser current per channel. In the middle section, we have iC-HN and HN3, both single-channel drivers with up to 1.4 amps or 2.8 amps of laser pulse current. And the 6-channel drivers iC-HG and HG30 currently mark the upper limit of drive strength with 1.5 amps or 5 amps per channel. Paralleling all 6 channels of iC-HG, for instance, gives you a maximum of up to 30 amps of laser current. All these drivers have a common, straightforward, rather simple architecture. It consists basically of a voltage-controlled current source and a very fast switch. A voltage here at Ci sets the output current through the laser diode, and a logic signal here at the switching inputs defines frequency, duty cycle, and pulse width of this current. So basically, whatever pulse pattern you want to have here at the output, you have to input here at the logic inputs. Our standard 8 by 10 centimeter eval boards are perfect for continuous wave operation or low to mid-speed pulsing. For high-speed pulses, though, talking of single-digit nanoseconds, the track length on the board here from the IC in the center to the terminals for the laser diodes at the edge of the board are simply too long. That's too much inductance in the laser current path for fast pulsing. So what it requires is a highly optimized high-speed module with an ultra-short track length between driver and laser diode. And if possible, a suitable interface on the bottom side of the board for attaching a heatsink. These DIL28 white body format high-speed modules come fully populated. You just have to attach your laser diode here at the edge of the board. The potentiometers here let you set the output current. Such high-speed modules are available for most of these nanosecond laser diode drivers. There's, for instance, the iC-HN on the HN1M and also for the iC-HN3 with a layout optimized for through-hole and SMD mounting here at the edge of the board. For iC-HG and HG30, actually there are 3 different modules available. One optimized for through-hole mounting, and 2, the HG20M and HG21M for SMD mounting with 2 different pad layouts for different SMD packaged VCSELs, for instance. For easy operation of these tiny high-speed modules, we strongly recommend our host adapter HG2D. These high-speed modules simply plug into the center of this board. The HG2D can actually host all our currently available high-speed modules. It has a two-channel setup here so that the multi-channel drivers can be operated with two different currents, for instance, one for biasing and one for pulsing. We have easy access to connect the supply voltages here at the bottom of the board for the IC and for the laser diode. The opening here in the back of the module allows access to the bottom of the high-speed module and thus enables you to assemble, for instance, a heatsink. Please do see our heatsink assembly kit available for the HG2D for details. Then there's also sockets here at the bottom, top edge of the board, which allow to directly plug in our pulse generators or oscillators. And these pulse generators and oscillators, Stefan is now going to introduce.
Thank you, Uwe, for introducing the host adapter and the high-speed modules, which give you the opportunity to evaluate our ICs with ease. To make it even more simple to generate short laser pulses, we have three different modules which attach to the HG2D board at the top. All three serve different purposes. Our main workhorse here is the iC-149, which you can use to adjust the repetition rate and the pulse length of the logic signal, which is then input into our high-speed modules and the IC itself. For higher frequencies, we offer our oscillator iC-213. This then only can change the repetition rate, but in a larger scope. But if you still need to adjust your pulse length while having higher frequencies, then the pulse shaper iC-245 can be combined with the iC-213 oscillator because this only shapes the pulse by prolonging or shortening the pulse length. So let's go into detail what our modules offer. The iC-149, the multi-purpose one of those, is the most commonly sold one. It has 1 to 64 nanoseconds pulse length available. This then is defined in 0.25 nanometers step size with this coarse and fine dial. So it's really that easy. Just with a turn of a knob, you can sweep your pulse length between 1 to 64 nanoseconds. If you then want to change the frequency or the repetition rate, how often your pulse is triggered per second, you can choose from a fixed 1 megahertz crystal option, or you can use the adjustable oscillator on the board here. And by turning this little potentiometer, you can go from 1 kilohertz, so a very slow repetition rate, which will result in a very small duty cycle if you have a short pulse. Makes this readily accessible. So this is the electrical features of it, but also important is that you can hook it up to your lab equipment. So most importantly, at the bottom you have the adapter interface for our host adapter, just a pin connector. And in the top left, you can see a trigger output, which is very handy, that can be plugged into the trigger input for your oscilloscope. And then you can get a nice correlation of the laser pulses to the trigger pulses. On the output side here, we supply LVDS and TTL output. There you can already go for your application requirements, as our ICs support mostly both of those. The IC-213 has a different range of frequencies. This goes up to 1.4 gigahertz and starts already at 40 kilohertz. And this is also set by those dials by hand or manually. There are 4,000 repetition rates preset, can easily be swept over. And it also provides the LVDS and TTL output at the bottom with the HG2D host adapter connector. It also features the trigger output for your oscilloscope triggering. And that's basically all you need to know about this. Please bear in mind that it has a fixed duty cycle of 50%. And if you want to change this, you purchase our IC-245 pulse shaper, which connects to the IC-213 at the top and to the HG2D in the bottom. As you can read here, this device has only LVDS input and output, but this is not a problem for our ICs. It will just work. Here, if you have attached this to your setup, it will offer pulse lengths from 250 to 10.2 nanoseconds in width in a step size of 40 picoseconds. Here again, we have our beloved dials where you can go in 40 picoseconds step size through this pulses range. It has a limitation of 200 megahertz repetition rate because we have to get the signal somehow in and out, and this is just a matter of length of the copper traces on the board. It also features the trigger output so that you can sync to the really outputted signal to the HG2D and the high-speed modules, and so you are more in sync with your application. So let's introduce Uwe again for the next segment.
Thank you, Stefan. This more or less completes our electronical setup. We have the high-speed modules with a laser diode attached with its leads shortened to an absolute minimum. This high-speed module then goes onto the host adapter, and we plug in one of the modules, in this case, the pulse generator. So, supplying appropriate voltages then to the board, we should be ready to produce nanosecond laser pulses. But how to validate that we really get what we want? We have to do measurements. The easiest thing to measure is, of course, what pulses are going into the driver. This is very handy, for instance, for setting up the correct repetition rate, duty cycle, pulse width, and so forth. But besides that, the pulses at the input, in particular rise and fall times, have no relevance with regards to the expected dynamic behavior of the output pulses from the laser diode. So for setting up the correct pulse pattern at the input, perfect. But for the correct pulse shape, we have to look at the output. The easiest way to do is, of course, hook up your oscilloscope probe simply to the driver output, measuring a voltage. But such a voltage is no proper image of the actual current through the laser diode, let alone the optical output. This is what we get here. And in fact, it raises more questions than it answers. What are these spikes here? What is this ringing here? Is this all real? Both is in fact caused by the residual inductance here in the laser current path. It's inevitable. It's simply there. And this is also why this voltage cannot be a proper image for the current through the laser diode. So, what then? Measuring the real pulse current through the laser diode is very tricky. The majority of current probes is simply too slow to measure single-digit nanosecond pulses. And inserting a sense resistor in the current path, preferably on the anode side, adds even more inductance to the laser current path and changes the dynamic of the pulses. So, in the end, what is it that is of interest to us? It's the optical laser pulse. That is the output of the laser diode. So, we have to do an optical measurement to really assess what is the shape of our generated laser pulses. To do so, a simple photodiode and a standard oscilloscope won't do though. What it requires is a suitable photoreceiver, which is fast enough to, for instance, capture all these effects here, which is, for instance, the gain switching spike and intrinsical effect in the laser diode. And the photoreceiver should also have no limitations in with this respect, and should not have any artifacts, as for instance a slow tail, which would be visible here on the falling edge, which would be a long, slow decay. Also, the oscilloscope should have a minimum analog bandwidth of 3 to 4 gigahertz actually. So Stefan, can you supply something along that line?
Sure, I can do. At iC-Haus we have 2 photo receivers, IC212. Both have a bandwidth of 1.4 gigahertz and they start to operate with continuous light, so it's DC to 1.4 gigahertz in respect for bandwidth. They of course have no slow tail effect and they are available for the infrared and for the UV visible part of the spectrum. So if you will have a laser diode, some were emitting from 320 to 1000 nanometer, you would go for the IC212 with the NST suffix. And if you have an infrared or near infrared diode, somewhere between 800 nanometers to 1800 nanometers, the IC212 NIR is the photoreceiver that you will need. Those have, of course, inputs for light. They are available as free space or with a connector for fibers. And the output, you have a standard SMA jack to plug in your SMA cable for your oscilloscope. Of course, you need a fast oscilloscope for that. We will come to our oscilloscope on the next slide. We have also included an offset compensation where you can turn the knob to offset any DC level to optimize your signal to your oscilloscope. And if you combine these photoreceivers with our sampling oscilloscope IC227 with a 11 gigahertz bandwidth, you see you have some room left. You for sure are going to measure a good signal with the 1.4 gigahertz bandwidth photoreceivers. the sampling oscilloscope we offer has a pretty compact design because it has no screen built in. All data is displayed via software graphical user interface on a connected computer. Standard USB port is enough to attach this. It also has a pretty attractive price in our opinion, as it's a direct sampling oscilloscope. It is quite affordable. So now we have all together to get a real experiment running. So our toolkit consists of the signal generators or oscillator pulse generator modules, the host adapter, which connects to the high-speed modules, a laser diode, and then on the other end of the optical path, we have here shown our UV visible photoreceiver connected to our IC-227 oscilloscope. And now it is time for the live demonstration. So I will move over to the actual setup in real. As I already explained, here we have all the parts assembled on our little mini bench top here. Signal generator is the IC-149, mentioned quite often. Then the host adapter board connected with two different voltages for the IC and the pulse generator, and the second voltage for the laser diode. Then we have encapsulated the laser beam in a little tube so that we have no stray light here. And the photoreceiver then outputs its signal just over to the little oscilloscope. As you can see, it's really not that big compared to most lab oscilloscopes that you are used to. I will now show you here some details of the laser pulse in our user interface of the oscilloscope. We have this gain switching spike at the beginning, only a few hundred picoseconds in length. After this effect is over, you see some ringing from the LC oscillations in the laser current path, and then we have a more or less steady light signal for the rest of the, in this case, 64 nanosecond pulse lengths. This is the maximum setting the IC-149 can deliver. So let's turn a knob and shorten the length of the laser pulse in turning this dial to like half of the length. Went smoothly. If I use the fine tune knob, as I am here displaying 10 nanoseconds per division, half of the screen is already 50 nanoseconds. You won't see a lot of effect because this fine stepping is so short that it's not going to do much. So this is how easy you can adjust the pulse length. Now to the features of the iC-HN. The iC-HN evaluation board has a potential that I can turn, and this will regulate the voltage that controls the current of the laser diode. Let's see if I can hook my little screwdriver up to it. Yeah, I grasped it. And now I'm going to lower it. You see you have a more pronounced ringing on the laser diode current path now, but it's also easy to turn it so down that we only see little spikes at the beginning. If I turn it back up, you see we are very reproducible in getting our signal back. So those are the main features what we wanted to show you today. A very compact setup to getting started with our ICs and try out different duty cycles or pulse lengths.
Thank you, Stefan. Very impressive how easy generating and measuring of nanosecond laser pulses can be using our toolkit. So let's sum it up. What is the tool chain we're using here? We have the ready-to-use high-speed modules on our host adapter with pulse or oscillator modules directly plugged in. We have a DC-coupled, no slow-tail photoreceiver and an 11 gigahertz sampling oscilloscope. And the best is they're all easy to use, as Stefan just demonstrated. And they come at an attractive price. So get your laser toolkit now and start evaluating and generating nanosecond pulses. That's all for today. Thank you for attending. So back to you, Henrik, for the Q's and A's.
Thank you very much, Uwe. Thank you very much, Stefan. Just want to make a little announcement on the beginning of this session. We had a little problem with the tone, so I apologize for that. But I hope you have got good information from us here today, and we will take your questions now. And I'll start away right now with you, Uwe. And first question I have here for you is, any recommendations on how to avoid or reduce the gain switching spike at the beginning of the pulse?
Yeah, well, there are several methods, but most commonly you would have to either bias the laser diode. This is what I introduced with a 2-channel design of the host adapter, that you could use a bias current and a pulse current, biasing the laser diode just around the laser threshold will suppress this spike. The other method would be slowing down the slope of your current pulse, but this contradicts nanosecond pulses, actually.
Okay. Understood.
The downside of biasing is, of course, that you have a lot of power dissipation in the driver then. And you have to find a trade-off if you really have to get rid of this gain switching spike in your application, or if you could live with it.
Okay, understood. Thank you. The next question is, you were referring to single-digit nanosecond pulses, but single-digit can be 1 to 9. So what's the actual lower range?
Okay, that depends on the individual drivers. Actually, with the introduced HKs, it's 2.5 nanoseconds.
Mm-hmm.
It's limited by the digital interface, in fact. And with HN, HG, HD30, and so forth, it's 2 nanoseconds.
Okay.
And if you're able to really produce 2 nanosecond laser pulses, even if you input 2 nanosecond pulses, depends on your setup, on the PC board layout, the operating point, the supply voltage, the laser diode itself.
Got it.
But that's the minimum that IC can process of input pulses.
Okay, thank you. Next question is, how can I achieve a closed loop regulation for the nanosecond laser pulse?
Excellent question. This picks up our whole measurement problem here, because for feedback, I would have to be able to measure either the pulse current or the optical laser pulses. As I explained, difficult, they're quite short. The best option you probably have is either measuring the average current entering the laser current path. At best, you should be able to measure the average optical output power. And then using the average output power, you could sample it frequently and then adapt the control input at the CI, for instance, because what you want to compensate with this closed loop would be mainly temperature effects, which are slow. So you can do this on a sample base.
Excellent. Okay, thank you. More questions. Are your hardware voltage-based or current-based driver, and why?
As I explained, the architecture is a voltage-controlled current source. So we're driving the laser diodes by means of a current, because current is turned into light. So, our idea was that we want to have highly scalable rectangular pulses, not Gaussian pulses, like with voltage driving, but rectangular pulses which can be scaled both in length. This is what Stefan demonstrated, and both in amplitude. This is what he also demonstrated. And this requires this type of architecture. This is why we choose the current drive approach.
Excellent. Okay, thank you. More questions? Can you comment on the temperature stability current?
Being an open loop driver, there is a certain temperature drift. So this is possibly why you want to implement a certain feedback loop to, for instance, stabilize the current, at least the current, at best the optical output power. But that's the downside of this open loop architecture. But as explained, a closed loop architecture with nanosecond pulses is very difficult to implement.
Okay, understood. I have two more questions for you. So can I use these drivers for continuous wave operation?
In principle, yes. This is why most data sheets of these drivers also state a maximum continuous wave output current, which is, of course, lower than the pulse current. But basically, yes, you just have to keep an eye on power dissipation. And because of temperature drift and so forth, you might want to have a look at our dedicated continuous wave drivers, which usually come with a feedback loop for either current or output power, which would give you a much better performance than these open loop drivers dedicated for fast pulsing.
Okay, got it. Thank you. So now the last question. Well, actually comes more in, so just keep on asking. It's good. We like it. So good dialogue. So what do you think about the laser pulses used in the encoder implementation?
I'm not familiar with that. I would need to see some examples of that.
Okay, we'll get back to the question here. Yeah, and you explained, but can you say again why you can't validate the electrical pulse shape?
My experience is that the majority of current probes that could measure the current in the laser current path without breaking the path are too slow for a single-digit nanoseconds. So your best option is to use a sense resistor, but you have to insert it into the current loop. You have to break the current loop. This expands the loop. This adds inductance, and this changes the dynamic behavior. I've seen this being done. If you can live with the downside of reduced speed, for instance, if you're going for not single-digit nanoseconds, but two-digit nanosecond pulses, this could be a good compromise there.
Okay. Good. I think I have the last question now here for you. So how do I suppress ringing in the optical output pulse and get a clean pulse? We are trying to generate 100 nanosecond pulse in which we see 10 nanoseconds consistent ringing.
Okay. Ringing is, as Stefan explained, it's an LC ringing. This is parasitic effect of the laser current path. So your design goal is to reduce both L and C. L, the inductance, can be reduced by shortening the laser current path to an absolute minimum. Same for the C, but the majority of the capacitance is presented by the driver itself, so it's difficult to reduce that one. This is why we offer different ranges of drivers for different current ranges. Okay. So you will understand that using a 30 amp driver doesn't make sense if you just want to drive 100 milliamps. Yeah. So basically, the ringing is more or less a result of your design. Possibly also the connectivity inside the laser diode and things you cannot really influence there. Okay.
I would like to add also that for your laser diode, it's important that you look at the diode housing. Sometimes the diode housing is connected to the anode or to the cathode, and if you have such a laser diode in use with the metal can having also some capacitance, then of course this will for sure add a lot to your LC ringing.
Exactly. Thanks for pointing out.
Okay, I think I have the last question now,
okay.
So I'll give it a go. So I don't remember the reference of the chip, but there was one exploiting the switching pulse with pulse widths in the sub 100 picosecond range. Would it be possible to demonstrate these thin pulses with the hardware that you just presented?
Basically, yes. If you have watched our last webinar on the iC-Haus for the sub-nanosecond pulses, where we reduced this pulse in a way that only the gain switching pulse was left. We used basically the same setup as we presented today, except for the photoreceiver. Okay. You will understand that for, let's say, 100 picosecond laser pulse, the 1.4 gigahertz photoreceiver is too small. But we're planning to release an even faster photoreceiver, which then can be used to also properly detect this gain switching spikes.
Okay, excellent. Good. This concludes the Q&A session. I want to thank the audience here for submitting really good questions. We will reach back to you as well on some of the open points that we had here, but really good to have a dialogue with you, our dear customers. So in that, I will like to conclude today's session. I would like to thank Uwe and Stefan for an excellent presentation, and we look forward to see you soon again. We will do further webinars in the fall, and just watch out for our invitations for those ones. And we look forward to have a dialogue with you again. So thank you very much. Bye-bye.
Bye.
iC-Haus. Integrated circuits.